Have you ever looked up at the night sky studded with countless stars and just wondered? Really wondered. You see the moon. You know the planets are out there tracing their silent orbits. Beyond them lie stars, galaxies, clusters of galaxies stretching farther than we can possibly imagine. It's a natural human impulse to ask the next question, the big one. What's past all of that? If you could travel in a starship to the very farthest galaxy we can see, and then keep going, what would you find? Is there a wall at the end of everything? And if so, what's on the other side? This question, in one form or another, has captivated philosophers, poets, scientists for millennia. It's the ultimate inquiry into our place in the cosmos. It challenges our everyday intuition. Here on Earth, every space has a boundary. Your room has walls, your city has limits, even our planet has an atmosphere that thins out into the vacuum of space. We are conditioned to think that everything must be contained within something else. So when we think of the universe, the grand totality of all matter, energy, space, and time, we instinctively try to place it inside an even bigger, emptier box. But what if that's the wrong way to think about it? What if the universe isn't in anything? The quest to answer this question isn't just a philosophical daydream, it's a central pillar of modern cosmology. It forces us to confront the very nature of space and time. To even begin to formulate an answer, we have to let go of our earthbound, common-sense notions of edges and containers. The universe might not play by the rules we're used to. It operates on a scale of size and time so immense that our brains, which evolved to navigate our immediate environment, struggle to grasp it. The journey to understand what lies beyond the universe begins with understanding what the universe is, and the incredible discovery that it is not static but growing. So let's embark on a journey of cosmic discovery. We'll leave our familiar assumptions at the door and venture into the strange and wonderful reality described by physics. We will explore the evidence that revealed our universe is expanding, what that expansion actually means, and why the concept of an outside might be meaningless. This isn't just an abstract thought experiment. Understanding the shape and fate of our cosmos gives us the grandest possible perspective on our own existence. It connects us to the vast unfolding story of everything. The universe is telling us its story, and we just have to learn how to listen. Before we can talk about the universe expanding, we need to agree on what the universe even is. In the simplest terms, the universe is everything, and I mean everything. Every star, every planet, every galaxy, every speck of dust, every beam of light, every mysterious particle of dark matter. It's not just all the stuff in existence, it's also the space that stuff occupies. More than that, it's time itself. Space and time are woven together into a single, four-dimensional fabric called space-time. The universe is the entire tapestry of space-time and everything embedded within it. There is, by definition, nothing outside the universe, because the universe is the totality of all that is. This concept can be difficult to wrap your head around. We are used to thinking of space as an empty stage, a pre-existing void where the drama of the cosmos unfolds. But according to Albert Einstein's theory of general relativity, this isn't quite right. Space is not passive, it's an active player. It can bend, it can warp, and as we'll see, it can stretch. Think of it less like a rigid box and more like a dynamic, flexible fabric. The planets, stars, and galaxies aren't just moving through space, their very presence shapes the geometry of the space around them. This is what we feel as gravity. The universe isn't a collection of things in space. The universe is the space, the time, and the things. So, when we talk about the universe, we're talking about the whole show. The observable universe, the part we can see from Earth, is a sphere about 93 billion light-years in diameter. This isn't the edge of the universe, but simply the limit of how far light has had time to travel to us since the Big Bang. It's our cosmic horizon. There's almost certainly more universe beyond our horizon, but we can't see it yet. For most of human history, we assumed the universe was eternal and unchanging. It seemed like a reliable, static backdrop to our lives. The stars were fixed in their constellations, a celestial clockwork that was predictable and constant. Even in the early 20th century, most scientists, including Albert Einstein, believed in this static universe model. The idea that the entire cosmos could be dynamic, that it could be growing or shrinking, seemed absurd. It went against all intuition and philosophical preference for a stable, everlasting reality. The universe just was, and it always had been, and always would be, or so we thought. The first cracks in this static picture appeared not through a telescope but on paper, in the equations of Einstein's own theory of general relativity. When Einstein formulated his theory in 1915, he was shocked to find that his equations predicted a universe that couldn't sit still. The force of gravity, acting on all the matter in the cosmos, should cause it to collapse in on itself. A static universe was unstable. It was like trying to balance a pencil on its point. To fix this, Einstein added a new term to his equations, the cosmological constant, to act as a kind of anti-gravity force that would prop the universe up and hold it steady. He later called this his biggest blunder. The real revolution, however, came from observation. In the 1920s, an American astronomer named Edwin Hubble made a discovery that would forever change our understanding of the cosmos. Using the powerful Hooker telescope at the Mount Wilson Observatory in California, Hubble was studying faint, fuzzy patches of light called nebulae. At the time, no one was sure what they were. Some thought they were gas clouds within our own Milky Way galaxy. Hubble proved that these nebulae were, in fact, entire galaxies in their own right. Vast island universes located millions of light-years away. This discovery alone dramatically expanded the known scale of the cosmos. But Hubble didn't stop there. He measured the light coming from these distant galaxies and noticed something peculiar. The light was stretched, or redshifted, as if the galaxies were all moving away from us. And the farther away a galaxy was, the faster it appeared to be receding. The conclusion was inescapable. The universe was not static. The distances between galaxies were systematically increasing over time. The entire cosmic fabric was expanding. This was the first observational evidence that our universe has a history, that it was different in the past, and that it is evolving. The eternal, unchanging cosmos was gone, replaced by a dynamic, expanding one. So how did Hubble know the galaxies were moving away? The key was a phenomenon called the Doppler effect, but for light. You experience the Doppler effect for sound all the time. When an ambulance siren is coming toward you, the sound waves get compressed and the pitch sounds higher. As it passes you and moves away, the sound waves get stretched out and the pitch drops. This change in wave frequency due to motion applies to light waves as well. Light from an object moving toward us gets compressed, shifting its color toward the blue end of the spectrum, a blue shift. Light from an object moving away gets stretched, shifting its color toward the red end of the spectrum, a red shift. Hubble and his colleagues spent years carefully analyzing the light from distant galaxies. They used a technique called spectroscopy, which splits light into its constituent colors like a prism creating a rainbow. Within this spectrum, they could see specific dark lines, which are the chemical fingerprints of elements like hydrogen, calcium. They knew exactly where those lines should be in the spectrum, but for nearly every galaxy Hubble observed, these lines were shifted toward the red end of the spectrum. This was the cosmic siren, telling him that these galaxies were all rushing away from us. The truly groundbreaking part of Hubble's discovery was the relationship he found. After painstakingly measuring the distances to these galaxies and their redshifts, he plotted the data on a graph. The result was a straight line. The redshift of a galaxy, and therefore its recession speed, was directly proportional to its distance from us. This became known as Hubble's law. A galaxy twice as far away from us is moving away twice as fast. A galaxy 3 times as far is moving 3 times as fast, and so on. This wasn't a random scattering of galaxies. It was an ordered, uniform expansion of the entire cosmos. So, what does it mean for the universe to expand? A common misconception is to imagine the Big Bang as an explosion in space, with galaxies flying away from a central point like shrapnel. But that's not what's happening. The expansion of the universe is an expansion of space itself. The galaxies aren't flying through space. They are being carried along by the stretching of the cosmic fabric. A classic way to visualize this is the balloon analogy. Imagine you have a deflated balloon and you draw a bunch of dots on its surface. Each dot represents a galaxy. The dough is the fabric of space. Now start inflating the balloon. As the balloon expands, what happens to the dots? From the perspective of any single dot, all the other dots appear to be moving away from it. The dots themselves aren't crawling across the rubber surface. It's the rubber surface, the space between them, that is stretching. Just like with the balloon, no single raisin is the center of the expansion. From the perspective of any raisin, all the other raisins are moving away from it. This model has some advantages over the balloon. First, it helps us visualize the expansion in 3 dimensions closer to the reality of our universe. The dough expands in all directions, carrying the raisins with it. A raisin deep inside the loaf sees other raisins moving away from it just the same as a raisin near the crust would. This reinforces the idea that your location in the universe doesn't matter. You would observe the same cosmic expansion from any galaxy. This is known as the cosmological principle, the idea that the universe is, on large scales, the same everywhere. The raisin bread analogy also helps clarify what is and isn't expanding. While the dough or space expands, the raisins or galaxies themselves do not. We finally arrive at the central question. If the universe is all there is, what is it expanding into? The simple, deeply strange answer is nothing. The universe is not expanding into anything. Into implies an outside space, a void waiting to be filled. But if the universe contains all space, there can be no outside space. Asking what is beyond the universe is like asking what is north of the North Pole. It sounds sensible but is actually meaningless given how north is defined. The North Pole is the northernmost point. There is no further north. Let's try to imagine this nothing. We picture empty blackness, a vacuum. But even a vacuum is a something. A vacuum is still space, empty of matter. It has dimensions. It has physical properties. It is governed by the laws of physics. It is part of the universe. The nothing outside the universe isn't empty space. It is the complete absence of space. It's the absence of time. It's the absence of dimensions. It's the absence of physical law. It's not even a place. It simply isn't. Language and intuition fail us here. Our experience is based on objects and locations within space. A reality without space is almost impossible to visualize. Cosmologists use mathematics. General relativity describes a universe whose metric changes over time. Those equations don't require an embedding space. The expansion is self-contained. The universe simply gets bigger. The universe isn't like a bubble expanding in water. It's more like the universe is the water. The amount of water increases everywhere at once. There is no not water for it to flow into. The expansion is a scaling up of the entire system. All distances between unbound objects grow. It's a mind-bending concept, but it's the simplest interpretation of our cosmological theories and observations. The universe doesn't need an outside, because it is its own self-contained, growing reality. Why should we care about these grand, abstract ideas? Whether the universe is expanding into nothing or space itself is growing, how does it affect our daily lives? On one level, it doesn't. Your breakfast will taste the same tomorrow. But on a deeper level, understanding our place in the cosmos is one of the most profound and humbling things we can do. It's about perspective. Learning about the scale and nature of the universe is a powerful antidote to our everyday concerns and our tendency to feel that we are the center of the world. We are not the center. We are, as Carl Sagan famously said, made of star stuff. We are not separate from the universe, we are a part of it. We are a way for the cosmos to know itself. And as we gaze out into the deep, we are not just looking at a distant out there, we are looking back at our own grand cosmic story.